David, and welcome Jan. And so Jan is a PhD student at Stanford University, working with Johan Ugander and a couple of other people here, and is going to talk about how to grow a graph.
Right. Thanks. Yeah, I wish I had thought of that original presentation format. That would have been much nicer. If my connection is bad, please speak up, because I can move to a better place that's less private but with a better internet connection. Yes, so I'm going to talk about work that I did with Austin Benson, George Pakapol, Supaniratisai, and Johan Ugander. And let's go. And the slides are available online, and I'll have them again at the end of the talk. Let's see, this works. Okay, so how do social networks grow is one of the oldest and most studied questions in network science. One of the, a common early method of doing this was observing a static graph and observing some outcome, some feature of this graph, for example, a heavy-tailed degree distribution, and then coming up with different hypothetical formation models that match on this observed feature. So for example, in preferential attachments, right, we also see a heavy-tailed degree distribution, and then we can hypothesize that maybe the graph was formed because of this process. Now, a big problem with this approach is obviously that multiple formation processes can lead to similar looking graphs. So it's hard to model fit and choose between different potential processes. So the main insight driving our work, which is fairly straightforward, is that knowing the ordering and timing of edges gives you a much better window into estimating these different effects that could potentially be happening. And in particular, that discrete choice theory gives a good analytical framework to disentangle the potential different mechanisms. So briefly, I'm going to introduce the discrete choice framework. I'm going to talk about two models, the conditional logit and the mixed logit. I'm going to talk about issues that happen when you apply these models on a large scale. And I'm going to briefly cover two empirical examples on real social media data. So I'll start with introducing the more general random utility model. So think of an agent I making a choice from available alternatives C, and I tries to maximize their utility. So they're trying to pick the item that has the highest utility to them. And the utility consists of a static component and a random component. And if we model the static component as a linear combination between some preference vector theta and the features of the item, and if the random component is distributed gumball, then the relative probability of choosing J can be thought of as the exponentiated static utility to that, the relative exponentiated static utility of that item relative to the complete choice set, the utility of the complete choice set. And this allows us to estimate the preference vector theta from the data. And this is relatively straightforward because the log likelihood is concave, and you can use many existing optimization routines to estimate this parameter. So if we apply this process on network formation, you can basically think of every edge as a choice, where the node I chooses between all the potential nodes that they can connect to based on the utility of the different nodes, and then forms an edge based on that choice. Sorry, I'm confused. I'm distracted by the chat. So just as an illustration, let's think back to preferential attachment, right? A very commonly studied model. In this model, the probability of choosing to connect to a node is relative to the degree of that node to the power of some unknown value alpha. And if we bring back the conditional logit formula, you can see that if you define a logit model where there's just one feature, which is the log of the degree of a node, then the theta that's being estimated is equivalent to the alpha from the preferential attachment model. In the paper, we go through a number of different formation processes and show that a lot of them can be written as components to a conditional logit model. And I say components because it's relatively straightforward to combine multiple elements together, so you can make much more general models quite easily. So as an illustration, we looked at a citation network, and we found that if you just fit a regular preferential attachment model, you get an estimate of alpha of about 0.7, so it's slightly less than 1. But if you look at the individual utility of having specific degrees, you see a few interesting things. One is that the relative value of the degree is indeed surprisingly linear. Like we were kind of surprised as how strong this relationship is. But you can do more interesting things. Like, for example, you can see that for lower degrees, there's actually a slight non-linearity. There's a slight elevated relative utility. And also you can estimate the utility of having a degree at all, which is something that's harder to do in a simple model like preferential attachment. And then you can make more complicated models where you start accounting for age, which increases the relative utility of degree. And you can keep going and basically start doing something like, regression models, like you see in, many social science work. For example, we found that having the same author really increases your chance of citing that paper, which probably does not surprise most of us. But that still may be an important thing to account for when you're trying to model something like citation dynamics. So let's move on to another model. There are a number of different formation processes that cannot be easily modeled with the conditional logit. And these are the kinds of models that say that there's a stochastic combination of different processes that are happening. This set of models, though, can be modeled with the mixed logit, which is basically something like a latent class model, where the different classes are different conditional logits with their own utility function and perhaps operating over their own choice sets. And they all have their own prevalence, their own class prevalence pi. For example, you can imagine that connecting to a friend goes through very different is a very different process that uses very different tendencies than connecting to somebody that you don't know at all, that you may meet randomly, for example. We show in the paper that the mixed logit covers a bunch of different stochastic models that have been proposed before. And one issue, though, is that the mixed logit is much harder to estimate because the log likelihood is not convex in general, and therefore you need to use expect EM, which is much slower and often not feasible for larger data sets. So far I've only talked about static graphs where edges are persistent, but all of this quite easily generates to modeling events on networks. For example, sending messages to somebody, sending money, interacting with content, or traveling between places. And the two main differences are, one, that you can often repeatedly interact with the same person. So the choice set is stable. It doesn't change when you make a connection. And two is you have to think a little bit more carefully about how to model time and how to aggregate past activity into features that are used on the moment that the event happens. So I've hinted a little bit of using these models on large data, and there's two things that at least two things, probably more, but we talk about two problems that happens when you apply this model on large data. One is that the size of the data, the construction of the data, and working with the data size gets really hairy because at every edge you can potentially connect to every other node. So the total size of all choices and all the possible choices n times n, which is often, obviously becomes really painful on really large data, really large networks. And furthermore, at every time step, at every edge being made, the features change or could potentially change, right? Because now, like every time a new edge happens, the features that go into the next edge can change. So that is really, the data construction is hard. But there's a second, more subtle problem, which is that the conditional logit model class is less realistic for large data. And that is because of the rational actor model. There's an assumption of complete information. The idea is that you need the chooser to be able to know all their options and also all the features of all their options, which is often not realistic for large graphs where you don't even know the existence of most of the other nodes in the graph. So I'll discuss both of these problems briefly. For the first one, the data size, you can use a trick we call negative sampling. There's many other names for it. It is a trick that occurs in many literatures. And basically the idea is that you can sample the non-chosen alternatives. and then do the same estimation on the reduced choice set if you adjust the likelihood based on the sampling probabilities of the different data points. And then it's an old and celebrated result that that the estimates on data on these reduced choice sets are consistent for the estimates on using the complete choice sets when you do this accounting for the sampling probabilities correctly. And there's different sampling methods that can be used. Uniform sampling is very easy because you don't even have to adjust the likelihood function at all. But this is a problem for rare features because, especially for important ones, like for example, if somebody is a friend, they are very likely to happen in the chosen item, but very unlikely to happen in the sampled non-chosen items because they're rare in the full graph. So to combat for that, you can use other methods, stratified sampling or more generally important sampling, and there's different pros and cons to them that I won't have time to go into now. But one thing that is kind of interesting is that there is kind of a theoretical question of like, is it better to work with smaller choice sets or with bigger choice set and fewer data points? And we don't have like theoretical results, but we do a few simulated experiments where we try to like find good trade-offs here. So to go back to the second problem of the infeasible assumption of complete information. So if we go back to the mixed logit, this is a perspective that does allow for modeling this a little bit better. You can, for example, think of they're just that, for example, for connecting to a friend, you have much more information and you can define a more complex utility function. Whereas for someone else, someone outside of that group, like you may know much less, maybe degree or maybe nothing at all, and it's just like a uniform a chance. But as I said before, these models cannot really be fitted on really large data. And also for the mixed logit, unlike the conditional logit, there are no sampling guarantees. So you can't really do negative sampling like what we can do with the conditional logit. So to solve this, we make a simplifying assumption that we define a new model we call the demixed logit, which is a mixed logit, but now every mode operates over a disjoint choice set. And this reduces the more complicated latent class mixed logit to m individual logits, which are all individually very simple to estimate, and you can use negative sampling, and everything's great. One intuition why this is so easy to do is that the choice, like if you look at the chosen item for every choice, because the choice sets are disjoint, the choice set that they're in indicates what mode that choice was made in. So you basically have a latent class model where the classes are known, and then you just have to estimate the utility function within those classes. So for example, in a message sending context, right, you can think of like there's a different process happening to send a message to a friend, a different than for a friend or than someone else. Like, and that's the sort of like setup that we use to analyze the data that we have. And just as an illustration, again, at every time step, like a node can choose between the local neighborhood or the rest, and that determines their choice set, which is generally quite small, much smaller than the full choice set. Very briefly, like we do a bunch of experiments on synthetic data. I want to show you this one case, which was kind of interesting, where we define a demixed logit, a model, we generate data according to it, and then we fit it with a conditional logit. So this is a different model class. And one thing that we saw quite repeatedly when you fit these models on data that's outside of the model class is that you get different estimates based on your sampling setup, which is not something that is theoretically supposed to happen within the model class. That's a nice reason why you can use sampling. But if you work outside the model class, you get these sort of inconsistent, unstable results. And that's obviously scary because that means that your sampling procedure will determine your outcomes. But we think that perhaps this can be used as a way of determining that you are working outside of the model class if you see this sort of behavior. Now, this is like all speculation. We don't have a good theory about this. And I should say that this is actually well understood. This is known as like the fitting of the data and the model and the model class is like a known condition for negative sampling to work. But this is not something that we've seen much used in empirical work. So we thought it would be worth reporting. So we we did some work on some data. So we scraped public transactions from Venmo. This is a data set of about 500 million transactions. About 70% are repeat between friends, and then another 7% are like from friends to friends. So this is a little bit of an indication of like this process happening at different scales. And we sampled this data down significantly, and then we fit a conditional logit and a demix logit to this data. I won't go, this is a regression table. I won't go into all of the details here, but there's a few interesting things. One is that the conditional logit, if you just fit a conditional logit, the role of the degree of the in degree is much less significant. Like it looks very small, but if you separate it out into the local and the non-local modes, you get this interesting pattern where, like, for the local modes, the local edges, there's actually a negative coefficient on popularity, and whereas for like outside, for people that you don't know, there's a strongly positive coefficient. And that kind of makes sense in the Venmo context, because there's a lot of large companies that many people interact with, which are, you know, like when you don't know them, like they of course, like their size increases the likelihood of connecting them. But when you have interacted with them before, you're generally much more likely to connect to people that are friends, that are real people, that tend to have a much lower degree. So this is a way for that coefficient to come up. And there's another thing that's maybe worth mentioning, is that in the conditional logit, the model basically tries to bend really hard to try to give a lot of weight to the fact that you are likely to send people to connect to people that you've connected to before. And I say bend really hard, like this estimate of 13 is you should think of this as the exponential utility. So x13 is the relative chance of connected to somebody with who you've interacted with before, which is obviously like very hard to interpret and not really workable as to interpret. And then last example, this is a work in progress. This is with Facebook college data. So the research question is, do people change their formation style like when they go to college? And what we do is we look at 100,000 individuals, and we fit a conditional logit model for each of them, for each individual, at each of 3 different time periods. When they're in high school, when they just enter college, the first 3 months, and then the rest of college. And then we actually have a 2-step analysis plan where we regress the conditional logit coefficients that we find on the school types of the covariates of the school that the person is going to see whether different schools induce different preferences and changes in these preferences. And you know, there's a lot going on here. Like you can see that obviously formation styles change like over time. There is some heterogeneity between different schools, like especially like elite schools tend to like have different processes than non-elite schools. One thing that you can see in the bottom left is that that only elite private schools, they start connecting to people of the same college much earlier, like during high school, than people in the rest. And you know, so we can start interpreting these covariates. And I just put this in there because of illustration of like how easy it is to apply this on really large data on a really large scale. And in this case, it's a little bit different because, like, right, we split it up by individuals, but still, like, there's there's like millions of edges that are going into these models. So to close off, so I hope I've convinced you that the discrete choice framework is a good idea for making estimating complex and interpretable models on large graphs. And I think the interpretable part is important. Like, we are interested in like trying to understand these dynamics. It's not necessarily just a prediction problem. Like, we want to actually interpret them because that allows us to use them in social science context. And yeah, there's a number of good features here, like is an intuitive mapping of utility. There's a lot of existing theory, so there's a lot of statistical tests for these models, and estimation is relatively straightforward because of negative sampling. But these models, they rely quite heavily on these assumptions, and they may or may not be adequate. And so thinking about those carefully is still, something that we have to do more of, and that we also want to encourage. There's more theory to develop on like the extent to which negative sampling is helpful in some contexts. And then if we could come up with better sampling guarantees for the mixed logit, that would also increase their applicability to larger data. There also, I should briefly mention that there's a lot of similar modeling frameworks in the sociological literature that generally suffer a lot from not being scalable, and they can only be applied to small data. But more empirical comparison and trying to match those two frameworks more directly to ours is also future work. So yeah, thank you. And yeah, these are the two papers that I discussed, and the slides and code are online. And
yeah, thank you very much, Jan, for an interesting talk. Keep the questions coming in the chat. We have actually plenty of time for discussion. And there you go. There are already 3. I don't know whether you can see them. We're just going to read out. So regarding the static setting, Jean-Gabriel asks, a lot of structural features of network correlate strongly with one another. This seems like this could lead to weak identifiability. So can you comment on feature engineering in this setting?
Yeah, so I think one of the advantages of this framework is that it should be more easy to compare the relative value of different structural features that otherwise would look quite similar. I guess I'm curious, like, what specific forms of correlation you are thinking about here.
So Gabriel says degree or age. I'm just
yeah,
gonna...
right. So yeah, so okay, that makes sense. So yeah, I think the way that would have to come out is that you have that you have coverage, right? That you see like data points where you have a high degree and a low age, or a high age and a low degree, and that right, like that you need a certain coverage of those two components to be able to then fit the model. And I have not thought a lot about doing a priori test on right whether that coverage exists in your data to be able to say something about identifiability, but that certainly is implied. Yeah, that you need to be able to see like data on different examples on different parts of the spectrum to be able to estimate the model for sure. Does that make sense?
I think the answer is yes.
So okay, so David, so was I surprised by why was I surprised by the nearly linear fit? Yeah, just how linear it is. I mean, like it could have been anything. And as we've worked through more examples, we've found more like slightly, bendy curves, but there's just like not a lot of variation. And I guess like it makes sense in the sense that, like, yeah, we shouldn't really expect 5 to be that much different than 6. So in a way, that is like, in a way it is sort of just a feature of like the relative difference being very small. But still, it was very, yeah, just like very often almost exactly linear. And yeah, I thought that I did not expect that. I thought it was much more likely to bend off, or to, I guess in some cases like to go steeply up, which we do see in some settings. And then Austin asks, for the Venmo data, do the estimated conditional logit and mixed logit models vary substantially on out-of-model predictions? I should check whether we have. I don't know why. Yeah, I have I have to go back and look at that. I feel like we have looked at we have looked at the just the predictive accuracy of the test and train set, but for some reason that didn't make it. I have to get back to you offline on that, Austin. And I like, this is not like a strong enough thing that I thought about to be able to just have the answer, because that should be a clear yes or no. That should be an answer hybrid. And I don't know.
Do we have more questions? Otherwise, while we wait for potential further questions, let me just say that the videos of all the talks are going to be online soon, hopefully on the webpage, where you also found information about this mini symposium. So we're looking to post those towards the end of this week, maybe next week. So just watch the homepage for further update.